In this video lecture, we'll discuss operations that we can do on extended Borel functions. And since extended Borel functions will be the main object of study in upcoming chapters, it is very important to know what operations we can do on them. We have classified the operations into two types. One will be sums, products, etc. And the other will be limits, lim_sup, etc. For the first type, sums and products and etc., we have two main properties or main lemmas, which is if we have two extended Borel functions f and g, then these subsets of omega, and we can read it in terms of random variables as well. If we have two random variables x and y and we have two events in omega, then these sets are at the set where f is less than g. And again, what is this? This is the set of little omega in capital Omega such that f of omega is less than g of omega, but we don't want to write this big every time. So the set where f is less than g, less than or equal to g, or different from g, these are all measurable sets. Before proving that property, let's state another one that will be proved using it, which is if we have two extended Borel functions, their product is always an extended Borel function. Remember, extended numbers can always be multiplied. Now, the sum of these two extended Borel functions, it may not be well defined for every omega. So now we have to make an assumption. The assumption is that it is well defined for every omega. How can it not be defined? Of course, is if we get infinity minus infinity. But assuming it is well defined, then their sum is also an extended Borel function. It is very convenient. We already know that if a function is from the real numbers to real numbers and is continuous, then it's measurable. That's very convenient. So we have already a large class of functions to start with, but the theory works also in the abstract. You don't need a concrete function to understand the theory. A different type of operations that we can do with measurable functions is when we take a sequence of measurable functions, then we can take the lim_sup of them, and we can also take limit in case the limit is defined. And this will be the following. The first lemma, which will be more of an auxiliary result, is when we have two extended Borel functions and we take the maximum of these two, or of course the minimum of these two, these are Borel functions. What does it mean, the maximum of a function? Well, we define age as the maximum of f and g. That means simply that for each omega, so this maximum here is taken pointwise. Pointwise means for each point. What is a point? A point is omega. So that means for each omega, age of omega is defined as the maximum of f of omega and g of omega. So the maximum of two functions, if this is f and this is g, then their maximum age will be this. This is the maximum of two functions. And what the lemma says is for two extended Borel functions, their maximum is also an extended Borel function. And now the most general result about sequences of measurable functions, it is we start with some measurable space. So note that for this week there is almost no measure or probability involved. We always have a measurable space and we want to do the operations there, and the measure comes after. And if we have a sequence of extended Borel functions, or extended real variables would be a particular case, then we can take supremum. So again, what does it mean to take a supremum of functions? It's just the function that to each little omega will associate the supremum over n larger than 1 of these numbers fn of omega. So this is what we mean by supremum of a sequence of functions. And then, of course, if it's true for the supremum, it will be true for the infimum. And we can also take lim sup. We like lim sup very much because every sequence has a lim sup, and the lim inf is a very robust concept. So, and all these are extended Borel functions. And moreover, if for every omega the sequence of functions converge, then the limit is also an extended Borel function. Of course, it will be an extended Borel function because a sequence of numbers converge. We know it. It converges if and only if the lim inf equal the lim sup. So if these two things are equal, and we already know they are measurable, then the limit, which is given by both of them at the same time, is also measurable. So let's go back here to this first basic lemma, which says the set of little omegas where one extended Borel function is strictly smaller than the other is a measurable set. Let's prove this before we stop this first part of this video lecture. So we're going to prove this, but let's assume this for now. If we know already that f, the set where f is less than g, is a measurable set whenever f and g are extended Borel functions, then we can exchange the roles of f and g, because this would hold for every f and g measurable. So if we exchange the roles of f and g, then we become g less than f is also a measurable set, and that means that g larger than or equal to f, which is the complement of the previous set, this is also in f, because f is a sigma algebra and sigma algebras are closed under complements. So this is all to say, once we prove this, then we get this. And once we have this, then we can also get this simply by taking the intersection. Yes, the set of points omega for which f is less than or equal to g. If we take the intersection with the set of points of omega for which f is larger or equal to g, and this is also measurable if we have proved this property. For every f and g, we just switch the roles of f and g in this statement here, and this intersection is exactly equal to the set where f equals g. And now, of course, if we take complements, then this becomes, the complement of this is the set where f is different from g. And so since this one is in the sigma algebra, this one will also be in the sigma algebra, and this one is in the sigma algebra because the sigma algebra is closed by intersections, and these two sets here, they are in the sigma algebra. So we have just justified that it is enough to prove just this. Now, to prove this, we notice the following. Whenever two extended real numbers are different and one of them is less than the other, it will be the case that for f of omega, this first number, if it is less than the second number, g of omega, that means there exists some q which is in between f of omega and g of omega. There exists some q which is a rational number. Okay? There is a rational number between the two, and this is really very important, because we can write now the set f of omega less than g of omega. We can write this set as the set of omega for which there exists a q. So this is a q. There exists a q, a rational q with this property, and we can write this as the union over all q rational, and this is something you see very often in measure theory. We are using rationals all the time but we're not using any particular property of rational numbers except the fact that they are countable and that they are dense all over the real line. So they are dense. Dense means every interval has rational numbers. So we take the union over Q rational, and this is a countable union. This is the important thing. You take the union over all these sets of omega such that f of omega is less than Q, and such that g of omega is larger than Q. Now we know this set here is measurable if we assume that f is a measurable function, and this set here is also measurable if we assume that g is a measurable function. So measurable means it belongs to this family. This family is a sigma algebra. It's closed under intersections, so we can intersect these two events here, to intersect these two sets. And so we get a set which is in the sigma algebra, and now we are taking a union, a countable union of them. So this will be in the sigma algebra, and this concludes the proof of this lemma.